Hey everyone. I just wanted to take a minute to go over the rest of this note packet. This was the note packet that we had started but never finished when we went out on break. So if you remember correctly, we were actually on this page right here where we were talking about global air circulation. And I actually had referred you to the reference tables. Remember, there was a similar version of this, right, in the reference tables on page 14. And when we had talked, we were talking about when air masses converge, and that gives us a low pressure or a wet belt, and where air masses diverge, which gives us a dry or a high pressure or a dry belt. We also use this to talk about convection all around the outside of our Earth because weather is really just unequal heating. And we said that most of our heat is absorbed by this equator, which is now tipped sideways, sorry. This is the equator of our Earth. And this equator is the hottest region of our Earth because it gets the most direct insolation or direct sun. And so that hot air rises up. And then once it gets away from the heat source, it cools and sinks, heats and rises, cools and sinks, heats and rises. So that's where we left off, is going through all of these different convection cells around the Earth, the wet and the dry bands that were really just low pressure and high pressure because the arrows were converging and diverging. One last quick review that I wanted to give you before I finish the note packet is this high and low. Remember, this is really just wind. So we've got wind is air moving from a region of high pressure to a region of low pressure. And remember the pressure, if we talked about the molecules themselves, remember they're just in constant motion and they bang into each other and they bang into each other and they bang into each other. And eventually they spread from high pressure to low where the molecules are more spread out. So this is just a natural occurrence. The movement from high to low is called wind. So when we left off, we were talking about air moving outwards from the high, outwards and then clockwise around the high, and inwards and to the right around the low, which gives it a counterclockwise motion. And even more so, we said at low pressure, this is where we get our cyclones. It's stormy, bad weather. And at our anticyclone, our high pressure, this is where we get our clear, sunny weather. So I want to take a moment and go all the way to the back page, and I want to do this little review with you real quick. It'll take 2 seconds because what this actually is an isobar map. Now it says at the bottom isotherms. That is a typo. This is actually isobars. I know that because these are barometric pressures right here. They're not temperatures. Good grief. If it was 1,016, we'd all melt. We would die. So these are all barometric pressures. And what I want you to do is I want you to take a scan of this and I want you to identify your highest and lowest pressures. And I'm going to start at the low, actually. I'm going to start right here. The lowest pressure I see on this map is 1,008. And so I'm going to connect those 1,008s in with a line, and that's called an isobar, a line connecting points of equal pressure. My next one that I see setting up is 1012 right here, 1012. So I'm going to go ahead and connect all my pressures of 1012 because those are all equal to each other. If I keep going up by 4, 8 to 12, my next line is going to be 1016, and this one's pretty clear also. This is a nice, easy barometric pressure map with nice, easy lines on it. All right. And then my next one heading up from there is 1020. I'm going to connect my 1020s. And then 1024. Now, one thing I see students doing a lot is a lot of people would see these 1016s over here and they'd want to just reach over and connect them to these 1016s, but we can't because there are no values. There's no data up here. So we actually can't connect those. Isobars would stop at the end of the map and that's where they would lie. They would just stop there and end right there at the edge of the map. The next thing I'd like you to do on this map is identify the area of high pressure and the area of low pressure. And we did this before we left, so we should all be set on how to do this. We know that in this little circle right here where it goes up to a pressure value of 1024, that's our high pressure. And this value over here of 1008 would be our low pressure. But it's a perfect time to practice drawing these lines. Remember how we start at the H and we go away from the high, but because of the Coriolis effect, it's going to veer off to the right. I'm going to spin my paper so that my H is always at the bottom of my arrow, out and to the right. I'm going to continue to spin my paper so that it's out and to the right, and then continuing to spin outwards and to the right. So remember how we said this was a clockwise circulation of air. So right over here in Utah and Colorado, they would be receiving nice, clear weather, and the wind would be blowing outwards in a clockwise direction in that area. The low pressure, remember this one being a little bit harder. This one, we actually have to move our arrow into the low, but it's still veering off to the right. So we're going to go in and to the right, and I'm going to turn my paper in and to the right so that I'm always drawing my arrow towards the low pressure. In and to the right, towards my low, in and to the right. And so we get this counterclockwise rotation of air here. And remember, this is Indiana and Ohio and Tennessee or Kentucky. I think it's, Tennessee and Kentucky. That would be getting sort of stormy, bad weather right there at that low pressure. So we've done high and low pressure. Up in this map right here, this is another review. This is going to review with us real quick. We're going to draw a horizontal line, which indicates where the air rises and cools to the dew point. So what I'm going to do is I'm actually going to draw my line in right here at the base of the cloud. Ooh, it's sort of scribbly. And at that base of the cloud, I know that right there, my air temperature equals my dew point temperature. How do I know that? Well, up in the sky right there, there are these little condensation nuclei. So maybe a piece of smoke or a piece of dirt or a piece of pollution or dust. And there's all this water vapor that's just floating around. And these water vapors actually start to condense around the outside of these condensation nuclei. So the water vapor, remember, is really small. And it's going to condense onto this condensation nuclei, and it's going to make a drop of water. So our water vapor is a gas, and it condenses to a liquid water on the condensation nuclei. And that's what's happening when the air temperature and the dew point are equal, and that's what forms the cloud. So that cloud is a bunch of these water droplets where the water vapor condenses into a liquid form. So it's water vapor all out here, but it's liquid water in here in this cloud, and that's what forms a cloud. The water vapor condensing into a liquid onto the condensation nuclei. And it does this when the air temperature is equal to the dew point. So what are condensation nuclei? They're little pieces of smoke or dust that provides a surface for condensation. So they provide a surface for the condensation. So the water vapor to condense on a surface. If you increase air temperature, how is relative humidity affected? This is a super important concept that lots of students have trouble. You're probably staring at it saying, I have absolutely no idea. I actually gave you guys an example, and when we did this in class, we had a little beaker here, and then that beaker grew to a larger beaker. Well, it didn't actually grow. I just used a larger beaker, right? I can't make a beaker grow. I'm not a magician. But we actually represented, each of these beakers represented an air mass. And do you remember we said that this cold beaker represented cold air? I'm sorry, the small beaker represented cold air, and this larger beaker represented warm air. And again, this is because cold air contracts and squeezes the moisture out, and warm air expands and has lots of room for water vapor. So that's why it's a larger beaker. And remember when we filled up this beaker to 100% humid, that actually, well, maybe it only filled up half of this beaker. And then as we continued to warm our air, maybe it filled up a third. And then maybe it just covered the bottom of this warm air beaker. So as we increase air temperature from cold to warm, what happened to the relative humidity? When the relative humidity was at 100% here, now it's only at 10. So as temperature increases, relative humidity decreases, which is an inverse or an indirect relationship. So as temperature increases, sorry, that's supposed to be an S, relative humidity decreases. All right, if you decrease air temperature, now we're going the opposite way. We're starting at this warm air and we're decreasing the air temperature to cold. So we're taking warm, we're decreasing it to cold. This is something that happens overnight pretty naturally when that sun sets. So how is relative humidity affected? Well, if temperature decreases, relative humidity is going to increase. There's that inverse relationship you see again. All right, so there's the inverse relationship. As we decrease our temperature, our relative humidity goes from really small to much, much higher. All right, last little bit. Wind. Wind is always named by where it's coming from. So you're going to see on another video that when we start learning about station models have these little circles with these little feathers on the end. And what we start to learn about is that this weather vane tells us where the wind is coming from. And this is the pattern of that wind. So if we think of this as north, and this is south, and this is west, and this is east, then this wind is coming from the southeast and it's going to the northwest. So it's coming from the southeast. So this would be considered a southeastern wind. It's coming from the southeast. A western wind would be coming from the west. A northern wind would be coming from the north. So let's take that concept and apply it to these pictures right here. Now, right away, if you look at the two pictures side by side, if we can do it sort of with my video, and you should be filling in these notes also, you're noticing that this one has a moon and this one has a sun. So this one is the sun. It's during the daytime. And this one has the moon. It's during the nighttime. So let's go ahead and start with the daytime first, okay? During a sunny day, we notice that the warm area is actually the land. Now, why is that? Well, the land is the rocks, the soil, the blacktop, the concrete, the sidewalks. And if you think about walking in bare feet in the summer, you can walk a lot slower in the grass than you can on the blacktop of your driveway because that black surface absorbs that sun really well. And so that's what's happening in this picture. The sun is shining and this ground here is absorbing that heat from that sun really well because it's dark in color and it's rough in texture. And so it's going to absorb that heat. Now we know that hot air rises, right? So this warm air is going to rise up above the ground and then it's going to move outwards over the ocean where then it's going to cool and sink, all right? It's then going to move across the ocean, heat up again when it hits this land, and rise. And then cool and sink. And then heat up and rise, and then cool and sink. Heat and rise, cool. You can see the convection that we've got here. So this is a convection current that we have setting up across this ocean and land boundary. So the cool thing is that when you're sitting on this beach, look at where the water is coming from look at where this wind is coming from during the day. This is our wind. It's the surface air movement. So our wind is coming off of the ocean, and we actually call this a sea breeze. So remember how I just said wind is always named by where it's coming from. If it's coming from the sea, it's a sea breeze. And so that's what's happening here. And I think in order to see this, we have to talk about the other situation that can happen, and that's right here. Now, if you've ever swam at night, it's like one of my favorite things to do. It's super fun because the water feels so warm and you actually like sort of duck down in the water so that only your head is sticking out because the water feels so warm. So at nighttime, the water is our warm area. And the ground, that dark, rough, textured ground, cools off very quickly, whereas the water retains its heat. Side note, why does the water retain its heat? Water has a very high specific heat, which means it cools slowly and it warms slowly. So it does everything slow. So in this case, it's still warm from the day, whereas the ground is cool. So the air over this warm water rises up and then it cools and sinks over the ground, warms up and rises over the ocean, and then cools and sinks. Here's our wind pattern now. Our wind is the surface air motion. So this is coming from the land and blowing out over the ocean. So we actually call this one a land breeze. A land breeze. And then the last thing for our notes for today, what happens to the temperature of air as it rises? Well, you already know this. You already know this. Temperature affects atmospheric, as air rises. You know this. The air cools. So air rises and air cools. So let's write that down. And then how does temperature affect atmospheric pressure? Well, remember how cold air has a higher pressure? And warm air has a lower pressure. But here's the thing. You probably just caught on to the fact that the high is down here and the low is here, right? We all know that to be true. We all know that this air right here with the high pressure is more dense and this air up here is less dense. So this is actually what drives convection, another really complicated concept in this unit. As this air warms up and rises, it actually cools because of this low pressure, which is what makes it sink and warm again. So even though this cold air has a higher pressure, this is actually warming up and then lowering the pressure. So it's all sort of this constant motion, and that's what drives the convection. So the air rises and cools because of the lower pressure, but then because of this lower pressure, it's going to now sink again and then warm up and rise again. So that's what causes that convection. And then I just remembered I wanted to just quickly do this last little bit here. I'm going to let you do the little practice here. I just wanted to make sure that you knew how to fill this in. So temperature, remember cold. So cold air contracts and is dry. And then warm air expands, and that allows more moisture. So warm air expands and is more wet, and cold air contracts and is more dry generally. Pressure, remember we have high and we have low pressure, and we know that air moves from a high pressure to a low pressure. And we know that low pressure is at higher elevations. So when we did this is reviewing from that time when we talked about low pressure being at the top of the mountains and how our Olympic athletes go up there and train at the top of those Rocky Mountains where they can get that lower air pressure, and that will make them a superior athlete when they go down to the bottom of the mountain with that higher pressure. They're going to compete better. And so a higher air pressure would be lower elevation. And then the last one, humidity. Remember, humidity is the amount of moisture in an air parcel. And when relative humidity is 100%, water vapor condenses to a liquid. And that's called dew point. So dew point is when that water vapor condenses to a liquid, and that's when relative humidity is 100%, or when the air temperature equals the dew point temperature. That's when humidity is 100%. So you need to be able to use the sling psychrometer to measure the humidity and the dew point of the air, and that's that chart in your reference tables. It's going to look really familiar when I show it to you. Your chart and your reference tables, just a quick review. It's this one on page 12. It's those charts right there that we were really good at using before you guys left me. So that should finish up that note packet, get you in a good spot to move on to the next thing, which is going to be station model creation and a lab. Talk to you soon, guys. Bye.